wrong answer, then I'm just guaranteed to be telling you the wrong thing 20%. I'm not incorporating information over time. So this idea that I'm going to try to clean up that noisy measurement, get rid of some of that jumping up and down that I would do if I was just using the current state, is called filtering. That whole idea. And if you take like a signals and systems class, they talk about low-pass filters and high-pass filters, and there's all these like partial differential equation stuff that you can do, and there's a lot of math behind that whole idea of filtering. And this idea of using a graphical model to do Bayesian filtering is a probabilistic approach to that. So when they created this model, they called it filtering because it's solving that problem. Like how do you clean up the noisy measurements? So who's are common filtering? Some of you guys? You guys are doing it on your project. That's another very common filtering algorithm. We'll talk about that today too. It's a more specific version of this Bayes. The Bayes filtering is the term Bayes filtering describes this very general framework for doing filtering, the problem of like cleaning up the noisy measurement by incorporating past history. From a probabilistic perspective, in almost the most abstract way possible, I think very minimal. Of course, you could have weaker ones than they make, but it's a very reasonable set of assumptions. It gives you a lot of power. And then using this basic model of Bayes filtering, there's been lots of different applications. We talked about sums, we talked about localization, and actually one change I'd like to make for next year's process. Last year we had localization as part of the project as well. And we swapped that out for SLAM. I think it would be helpful if you guys did for next year to do localization and SLAM. So you can see the filtering applied in those different cases. But still, we talked about localization in lecture yesterday. And I'm going to talk today, and we also showed you that video of the communication filtering. Where the robot, you're talking to the robot, and it's doing basically filtering to try to figure out what the person is. Again, you can see why the history might be important. If I was just making an estimate based on my current observation, I'm going to be like jumping all over the place. As a person gesturing like this, my estimate is going to go crazy, right? My observation is going to be very noisy. But if I just take a little bit of that history and incorporate it, I can do much, much, much better. So like if you've seen people doing sort of my mental model of like what filtering, problem that filtering solves, is like you've got, let's say you're a robot and you're trying to do position estimation. And you don't do filtering, you might think your robot is doing this, right? So it's kind of generally, you can see that there might be a mean here, like if this is my robot driving in X space, but it's very noisy. So filtering is like, what's really happening, despite this noise, is a smooth thing, right? That's really what I'd like my guy, that's really what I think is happening. So filtering is going from the noisy thing to the smooth thing. Okay, does that help? Thanks very much. Okay, so this is basically a summary slide of where we've gotten so far. So we've talked about Bayes filtering as one common graphical model. Of course, even that Bayes filtering as a graphical model, there's many, many other graphical models. We're going to talk about other graphical models in the rest of the course. So next we're going to talk about negative-based classifiers and logistic regressions. We'll talk about how the same probabilistic framework, which we could use to write down a Bayes filter, and then we can make assumptions and get to the probabilistic theory math. We can start in that same place with these graphical models and assumptions. And then we can make different assumptions about our problem and do some more scary math. Anyway, some more scary math, kind of hairy math, and get to classification. So this unifying idea of ties a lot of different areas. That's why I want to focus on it in AI. So it's called applied AI. So I want this idea of these graphical models, these ways, this probabilistic reasoning more generally, these ways of reasoning about uncertainty, and then see how they are applied in different ways. So in robotics, we state estimation, in machine learning, and text processing, to do classification, in reinforcement learning, to use state and sequence. All right. So we talked about this idea of the distribution, and then there's how do we represent the distribution. So we had CPTs, conditional probability tables, last week, and that's kind of my go-to representation. If I'm confused about what somebody's doing, I try to think about how would you do this as a CPT? What would the rows and columns be? How would it all fit together? Even if it's a very coarse approximation, there is some tracking. And then today we'll talk a little bit about but those are tricks that people play to make things scalable when CPT is too big. And then I just wanted to throw up there that there's these other models, H&M, Markov models, value-based classifier, topic models for classifying text and finding topics. So we're using a topic model in my lab right now to read a cookbook and look at ingredients in different recipes and find the topics. So topics are things like baking stuff, and the ingredients that go with the baking topic are things like bread, and flour, and milk, and yeast, and cornstarch, and baking powder. And other topics are things like stir frying, so you've got soy sauce, broccoli, and things like that. So like these models, these topic models find these kind of clusters. They're used in large test data sets. There's a really interesting one actually that works across time. So you've heard of Nature. Magazine, the journal, very famous journal of science, more chemistry and biology, relatively few science papers. But like, if you're a chemistry or a biology person and you have a Nature paper, you're basically guaranteed to get that. That's like everybody's goal. So they ran a topic model on Nature. It's very old, it's been going since like the 1880s. And they ran a topic model on all of the Nature articles, and they tweaked it so that it changed according to time. And so they got like topics for physics terms where the vocabulary, the technical vocabulary in the field has changed over the past 100 years. But it sort of changed gradually, and there were these overlapping pairs of words, and they identified these underlying areas that were in this discussion. You can go look that up. I can use some other talks about that. The time that you have between now and then is great. But I just want you to know there's other stuff out there besides statistics. So today's class what we're going to do is talk about deseparate. It's a technical thing about graphical models that is on your homework, and I didn't fit it in last time because I feel like the intuition, I wanted to get the intuition across and the idea of conditional independence. Deseparation is sort of a heuristic or an algorithm that you can use to figure out when things are conditionally independent of other things. And you can prove that it's right from James, and actually one of the problems of the book is to write out that proof. But what I want to do in class today is just say what it is and give you a little bit of the intuition of how it works. Then we're going to talk about SLAM. So we will go through the high-level math of fast SLAM. There might be a little bit of a review from what was in the SLAM review session, the SLAM session last night. But I think it's good to hear it again, maybe in a different perspective, to really try to give that high-level story of SLAM. And I've also got a graphical model of SLAM, which we'll go over these slides for. So that one, I'll think of also. Level thing. Then we're going to talk about our research results that came out that we were working on last year. That's from the generalization of SLAM. Again, so you can see how these apply in other settings. And then we'll finish up with a review of, I'm planning on like 10 minutes of just a review of the topics that we covered in the course and which you should be focusing on. I almost think it's a little better that we don't have the whole class for review because I think the best way to study is just so I'll talk it to you a little bit and I'll open the floor for questions about anything that was confusing, and there'll be more about it in my office hours tonight. But I think the best way to study for this test is to go through problems. So, and we're working on the practice material. But anyway, there's plenty of homework problems, and there's plenty of problems in the book that you can look at. So I recommend you guys spend any sitting here tonight time you have. Okay, so let's any questions before we begin? It's a little eclectic. All right. So deseparation. So Bayesian around. So D-separation is the full definition. Each node is conditionally independent of all others, given its parents, its children, and its children's parents. Okay? So this is a picture of that. So this is X, and it's kind of the thing that I think is kind of intuitive that like if I want to make X be conditionally independent, I've got to know the values of its children. Right? If X is going to affect whether Y is on or off, and I want to separate it out, like I need to know the value of Y. Similarly, if U is going to affect whether X is on or off, I need to know the value of U. I need to know the value of U to look things up. The thing that's a little unintuitive is this guy. Okay? So this is Z, which is the parent of Y, the children's parent. Okay, so I go down to the children and then up to the children's parent. This is double hop. It's a little weird. So we're going to try to see why this is necessary in an example, but you can also prove that it's necessary, and one of the problems the book has that as a problem. So prove why this is true from some of the problem. Basically, you write down the definition of conditional independence and show that you need it. So here's an example. It's kind of a famous one that was modified a little bit of a simpler graphical model with so many tools. So the idea is these are the different variables. So the graph is convenient with this screen today. So the idea is maybe the jet stream is doing something and that makes it cloudy or not cloudy. Maybe you did a rain dance and that caused the rain to come or not come, or you see the clouds on those airplanes or something. Anyway, somehow it's cloudy or it's not cloudy. And then based on whether it's cloudy or not cloudy, you might decide to run the sprinkler and it might rain or not rain. And then based on whether these two things happen, the grass is green. Okay, so like if the sprinkler is on, the grass is probably wet. If it rains, the grass is probably wet. So both true is probably wet. Neither is true. Okay? That kind of makes sense. And we could write down, maybe we should write down the model of this joint distribution. So how are we going to do this? Let's define some variables. E of J, what's the joint? What's the unfactored for a joint? It's probability of what? Not a trick question. Yeah, R. So what's R? Yeah. So let's use the variable R. What's that stand for? Yeah, rain dance. R. What else? What else? The unfactored joint.
J.
Yeah, J. What's J?
Jet stream.
Jet stream. I remember that. Good.
Okay.
What else?
C.
C. And say what chance.
Cloudy.
Cloudy. Yeah, good. Not a trick question. Yeah. Yeah. S. Yeah. Let's say let's call this R. Let's call that D. Dance. And then we can have R. Rainy and W. Grass. So I'm just making up variable names, of course. This might seem inane, but I think it really helps to just write out the joints equal. So now equals something. So now this is specifying a factorization of this joint distribution. Okay? What is the factorization? Can you guys read it off the graph? Start from the top and work your way down.
Probability of J times probability
Yep.
of D times probability
product. The graphical model is telling us, oh look, you can cross out lots of things. When we write probability W, we don't have to write it given S, R, C, J, and D. We can just write it as S. So that's the independence question. All right, so now let's think about sprinkler. So sprinkler, we want to know what things we need to know in order to make it conditionally independent of all the other nodes we have. Okay. What is it, and what nodes deseparated from the other word for this? We have this Markov link. What nodes are in its Markov link? So if I know the values of those nodes, I don't need to know anything else. The values of none of the other nodes, it's independent of all the other nodes. Knowing other nodes will not tell me anything more about the other nodes. So for sprinkler, what is the Markov link?
Cloudy, rain, or
Yes. So the parents, which is cloudy, the children, which is wet grass, and rain. So let's take each of those individually and kind of see why it needs to be there intuitively. So for cloudy, if I know cloudy, do I need to know jet stream? According to this model, no, right? Maybe you don't believe this model. Maybe you think there should be a line between jet stream and sprinkler. Maybe the sprinkler is in a computer program and it looks up on the weather forecast to see where the jet stream is and decide whether or not to turn on. That could happen. You could break that. You could create that technology. But because of the way this model is written down, we're saying the sprinkler, our sprinkler has a light sensor. It looks up at the sky where it is and sees whether or not it's cloudy or not. And that's how it decides whether or not to turn on. So cloudy, if I know whether or not it's cloudy, the jet stream doesn't matter. It might be that I live in Arizona. Okay? It might be that it's very unlikely for it to be cloudy. It might never be cloudy in Arizona. I don't know. But I know that they get a lot more sun than they do here with this kind of range of drizzly weather. So it might be very unlikely that the sprinkler would be turned on any given day. But once you know it's cloudy, or that it would not turn on, say it turns on when it's not cloudy. Once you know it's cloudy, you're in a different world. You're in a world where, as unlikely as it is, there's a big drought out in California right now, and we're all worried about it. But as unlikely as it all is, it's cloudy today, so that means knowing that I can predict something about this weather. Okay. So the parent, I think the parent is almost the most intuitive one. Like it's just writing out the CPT. Right? I have a table that says P of S given C is right here in my factor, which is CPT. So now let's think about sprinkler and wet grass. So this is sort of like our localization problem, right? Like maybe I don't get to know whether the sprinkler's on, I just get to know whether the grass is wet, or I want to know whether or not the grass is wet. Well, in this case, I want to predict whether or not the sprinkler was on, given that I've observed that the grass is wet. So does that make sense that they would tell you something about, yeah? Like if the grass is wet, like if the sprinkler's on, the grass is probably going to be wet. So if I see that the grass is wet, cross out rain from now, I can kind of imagine the sprinkler's probably full. So now, and maybe not cross out, let's imagine, so now let's think about rain, the children's parents. Imagine that we know that it's not raining. Okay, we know it's not raining. And we observe the grass is wet. Do you guys think the sprinkler's going to be on? Yeah, right? So this is called explaining away, right? So now imagine the other case. I know that it's raining. I know it's raining. And I see that the grass is wet. And you can even forget about cloudy and the rest of it. I see that the grass is wet. Do you think the sprinkler is on or off? Does that change what you think about the sprinkler? Knowing it's raining versus not? Yeah. So you want to say why your reasoning changes? Intuitively? Yeah.
If you don't know anything about the rain and you see wet grass, it could be either the sprinkler or the rain.
Yeah.
Once you see that the grass is wet, you have less.
You know it's raining.
Right.
Right. So you know it's raining. You have a reason for believing that why the grass is wet. So you can explain away the sprinkler. So even though without knowing rain, that might make you think the sprinkler is on. Once you know it's raining, your probability of sprinkler goes back down. So that's what you'd like to have happen. And that's what does happen if you work out the math localization in discrete environments. Now we're going to talk about what you need to do to extend these ideas to simultaneous localization, to SLAM, and functional testing. So the first thing I want to do, this video was not showing me the slide. This is an example of a SLAM event. The robot is driving around in the environment. It's building a map. It's maintaining hypotheses over trajectories it could have followed. So as it's going around, you see the map kind of jumps up and down as the estimates are kind of converging. Then it makes that loop closure, and it's like, oh yeah, I got back to where I started. And just closing. So this is LiDAR sensor. This is a LiDAR sensor. So you can kind of see the 2D occupancy. Blue is right out of space. White is free space, and black is obstacles. Okay. And we talked about it. So the other paper we're going to talk about today is the generalization of this work to do semantic mapping. So you guys are working with occupancy grid maps where it's just occupied, unknown, or free space where I can go. This is sort of more what the field is moving towards, where you're not just doing occupied free space, but you're actually giving the robot a tour of the environment. Here the robot's following the person with a robotic wheelchair. All right, so he's saying we're at the elevator lobby, and as he's talking, it's doing the same kind of SLAM. We're not drawing all the paths and stuff, but like it's building the occupancy grid map, the overall map over there as it's driving around, using very similar technology to what you guys are implementing for your class. But it's also, as he's talking, it's adding flags for labels. So like he's saying, we're in the hallway. Then it adds a little flag that says we're back in the hallway. These distributions, those little pie charts up there, are multinomial distributions over the labels associated with each distribution. So now he's going to say the gym is down the hallway, so we're giving this this relational expression, and it's incorporating that into the map complex language in order to do loop closure. So like it's able to fuse this semantic information with the metric information in order to make an overall map of the environment with labels of where stuff is that the robot can then use later to follow instructions or fetch items. So we'll talk, first we'll talk about sort of classic fast SLAM that you guys are implementing, then we'll talk about this. And I think it'll help maybe to see how these ideas have been extended or generalized. So that's why I'm including that. Okay. It's fast. So here he's going outside. He gets lost when he goes outside, right? Because there's no walls. The LiDAR is just maxing out its maximum range, and it's like, I have no idea. So it's just using odometry. How many times do my wheels turn in which directions, where it is, and the error there builds up. There's a little bit of error every time it moves, and as it builds up, it gets more and more. This is a tour. It's not the whole campus, but it's inside one building, completely the lobby, and then outside, around the building, and then back inside. There exist data sets of almost the entire MIT campus. This is at this data center at MIT. The largest data set I know of goes like down the Infinite Corridor, which is like several different buildings, and then go out down the Warren back across the court. They also actually have a data set of the entire data center, where they drove some poor graduate student drove a robot around every single building, every single room of all 8 floors of the 2 towers of this data center. Collected LiDAR data, image data, and odometry data to use in testing. You guys are doing a relatively small tour for the project. This is a bigger tour than that. But the sort of state-of-the-art in SLAM is pushing in a couple of directions. So one is much, much bigger tour. So like the entire campus, or even over time, like the city that you're in. Like as the robot operates in a home over a long period of time, and as things have all this type of information in my map in order to make plans, in order to do search, whether let's say run for search or A-star search. You can think of this as trying to construct that search space. And then also incorporating human interaction. So like this is an example of that. The person saying things, you want the robot to incorporate that information into its estimate of multiple. Okay. All right. So how can we do this? Maybe we talk about it in class a little bit. You guys have been in your project kind of thinking about this, but maybe it's good to take a few minutes now in class, talk to somebody sitting next to you, and think about how you would do. Let's just take SLAM as an example. So I've got a LiDAR sensor. I don't have a map. I'm trying to do localization and mapping. And think about how you would solve that problem. And then we'll sort of go through the slides. Take like 2 minutes.
We just have like a series of instructions. We don't like having like a session in the hour. So we still have a series of instructions to do with. I guess I'm not sure because if you have a sensor that tells you where the walls are, it doesn't tell you what to do. If you don't know where you want to go, right? You just roll something. So you're still being told where to go, like the control of your planet. I'm not sure what would change. Otherwise, I guess you could try to figure out if there's somewhere you can see before. Or like when you add a landmark, you know like where the walls are, and then if you like see those walls in that pattern again, then you're probably back to the same place. That's actually pretty good. Same way we do like probabilities, 2 landmarks are the same, we do probability, these walls are the same place.
Why would that be? How can we do
But
SLAM?
it's probably
Yes.
kind of alternate between like observation and moving.
Right. So we somehow want to separate the map. The map and I kind of want to alternate. Maybe I want to estimate one. Like there's a lot of problems break down this way. This is also like the EM algorithm, and even variants of this that aren't EM. Like this idea that like if there's two things I want to know and they're related to each other, what I do is this alternation thing. Like I separate the two things. So instead of just saying I want to know everything, oh my god, what do I do? I say, well, there's two things I want to know. I want the map. I want to know where I am, or my trajectory through the map. And if I had one, the other thing would be easy. Right? If I knew my trajectory for sure, and I had all my observations, I can figure out where the landmarks are. So all I have to do, maybe I have to do filtering, like localization, reverse of localization filtering. I can like say where I think there's landmarks are. The reverse of that is also true. If I know where all those landmarks are, I'm back to localization. Discrete mode, but like I can know my trajectory through the map. So I'm just gonna by separating these two concerns, I can exploit the fact that they inform each other. They're kind of, they're not independent of each other, but there's these two clusters of things I want to know. Where if I know one, then I can estimate the other. If I know the other, I can estimate the other. So that's the Bayes filter recursion. A lot of time, what's tricky when you're trying to apply this to a new problem is figuring out what those two things are that you can separate and give you realistic. So like the localization and mapping version of this is like the two things are x sub k or x sub t, the position and orientation of my vehicle at time step k, and z, m, which is the true m sub I for all of the landmarks, the true location of landmark. Usually when sort of in classic SLAM, there's this big elephant word that people usually just assume it's solved. Does anybody know or run across that elephant in the project that maybe made you question whether this is realistic? What's the elephant in the room? So I get to observe the distance and heading to landmark I in step K. Anything give you pause about that? We're talking about LiDAR. Yeah.
Well, you're able to recognize a landmark.
Yeah, so the elephant in the room in this model is, well look, I'm assuming that from my LiDAR readings, which are like I used to be 180 degrees at 1 degree intervals, I get a range sensor reading. Somehow from that, I'm able to get the distance and heading to landmark I. So I get to know that I've observed landmark I, and I get to know its distance and heading. How would I get that from LiDAR?
Kind of have to infer it based on the readings that you have.
Yeah, I look for like local patterns of features in the readings, right? So like maybe like a corner where it goes back 1.5 feet and there's some smooth wall around it. I can look for that pattern in the LiDAR. I basically do feature extraction. In classic SLAM, that is assumed to be given to factors. So this confused me a lot when I came to SLAM, because I thought, well, how do you get data? How do you get this information? The problem of doing this is called data association. Once you get your sensor reading, how do you take a feature and identify that it goes with this position? Okay. So you guys have some code provided to you in your project that does data association. Converts those raw LiDAR readings into these features that you can actually plug into the model. So like many times when you're reading or studying one of these problems, there's other problems that aren't part of it, or maybe they should be part of it, but the model doesn't try to handle it. The answer is kind of magical, right? There's some hacky thing, maybe, or maybe not a hacky thing, but there's some other research paper, some other deep technical thing that might need to happen in order to run this algorithm, this feature extraction. So when you're trying to understand these algorithms, it's important to identify them and decide whether you care about them or not. And if you don't care about them, accept that it's complicated, accept that you might not understand it all, and figure out what the abstraction barriers between it and the model that you're trying to understand. Okay. So then what we want to know is probability of x of k given, and also all of my map locations, given my control, my movements, the movements I made, and my observations. So here is sort of classic Bayes filters. Okay, so this is from last time. We had the measurements, the controls, and the z's. And we want to know a relief of I'm doing SLAM, what else has to be in the state? The landmarks, right. Okay, so let's pretend that I did that. I just redefined my X of t so that it includes the position, heading, and all the landmarks. And every time step it evolves over time. Does that make you happy or does that make you nervous?
When you say it includes landmarks, do you include all landmarks like currently sees or the
All landmarks. So the location of the landmark at time t, and then at time t plus 1, and then at time t plus 2. And I'm assuming a static environment. Does that make you nervous that I'm stuffing the landmarks inside the X of t's? Yes, why? Yeah. Yeah, my state space just got a lot bigger. Already it's going to get bigger because it's a harder problem. But I'm typical SLAM makes the assumption that my landmark locations don't change over time. Right? There's a fixed map and it's not going to change. I'm going to move around in the map, but it's not going to be like moving around me, even though that's false in real life. So if I stuff my landmark, my map, inside the state, if I just stick it inside X and T, that is an accurate description of what I'm doing, in the sense that it's a more general problem than the one that I'm actually solving. There's an assumption that I can make that makes that fast line moves. That makes your life easier. So what does anybody want to try to say what that assumption kind of reading? Anybody have thoughts about what that assumption might be? Yeah, the assumption is sort of like that my landmarks don't change. Like what can I do when I make this model as a result of that?
So storing landmarks in states, we can have landmarks somewhere else.
Yeah, that's right. That's right. So instead of stuffing them inside of X of t, I can have one set of those landmark variables, and I can write them out, and I can pull them out, and they impose their own independence assumption. Okay. So that everybody think that's cool? See why you might want to do that because they don't change. So if I pull them out, I can have one set of variables for the landmark instead of a set of landmarks at X at t and at t minus 1 and t minus t equals 1, t equals 2. Okay, so I have one set of variables, fewer variables. So imagine I'm doing that. What do the landmarks depend on? So I'm going to draw some nodes for my landmarks down. Where should the edges be? There's going to be 1, 2, I landmarks. So they don't depend on t. They don't depend on t. Yeah.
Well, your landmarks are dependent on your state, so like you'll observe different distances to them, or different landmarks based on where you are.
Yeah, so is it going to depend on the state or is it the observation?
Or observations.
Right. So let's do it. So my observation, so I'm going to pull out my M's. I'm surviving a bunch of them. I'm just drawing one of these weird abstract graphs. My observation now doesn't just depend on my location, it also depends on where all those lines are. Okay? So this is the graphical model for SLAM. I've got my control input, and I've got my X of k, which here is just going to be my pose, my position, and my orientation in the 2D map, which is changing over time. And then I have my observations, which are also generated every time I step. And then I have my fixed set of landmarks, which are 100 landmarks in that set. And their locations are static. I'm assuming that they're true. I might not know their locations, but I'm assuming that those locations do not change over time. Okay? They're fixed. So that lets me say, well, all of these observations depend on the landmark location and the state. There's this nice independence there. I don't have to stuff everything inside the state and give you this extra credits. Okay. All right. So then you can sort of write out, just like we were doing Bayes filters before, you can write out the time update and the measurement update for this. So probability of x of k and m, I'm trying to estimate those two things. And I get this integral, so this first term looks like localization. It's the state transition. Right, what's going to happen when I move. And then the second term is, the second term is your observation model, and it's predicting your map. It's the probability of your map location is given through history observation. map from last time, and maybe they're somehow merged. I'm trying to find the transforms. You can imagine that problem, right? It's kind of like localization, right? Like I've got these two maps, I want to align them or overlap them or something. But for the purposes of our project and make our life easy, we're just going to say, look, we're making this map for ourselves, and we're just going to define 0, 0 to be x. After that, as I move, I'm going to build up error, and I wouldn't even know how to get back to 0, 0. I've got a really noisy geometry system. And I replay my movements backwards, I might not end up exactly where I started. But I can at least know that that was defined as 0, 0. Does that help? Good question. It's very good to think about it when you're trying to figure these things out, how to initialize the algorithm. Where does how does that first state get picked out? And then how does it improve? Okay. So to do this efficiently, we can't use CPTs because the size of them is far too large. If you're talking about you're driving this guy, even around the CIT, it's too big to try to discretize this and write out a CPT. So one thing you could do is decide that everything is Gaussian and see what that takes. So that's called Kalman filter, extending Kalman filter. Don't worry about the difference between Kalman filter and extending Kalman filter. The idea is sort of like you can actually use the idea of a Kalman filter for localization as well. The idea is we're going to say everything is Gaussian. So we're going to say that my control function is some deterministic function of my current state, my old state, and my control. So if I'm a robot and I'm driving, and there's going to be some noise to produce in case some Gaussian noise. So now imagine that I'm a robot and I've got some odometry or something. What might f sub k minus 1 come to? I'm a little mobile robot, I've got some wheels, and I can drive forward. What might that be? It's deterministic. You don't need any probability. You're just trying to make your best guess about it. What's that guess? What's the input? Let's pretend, like, go back to your question. Pretend we're at the very first state, the first time step, 0, 0. So what's the input? Yeah, 0, 0, and then what's u? Let's say I'm going to drive forward. I'm going to turn my motors on for 1 second, and my robot speed is 1 meter per second. That's my control. So now what's f going to look like? I'm at 0, 0, and my control is I turn my motors on for 1 second at 1 meter per second. What's that? Yeah, it's a new position, right? So let's say I'm facing, like, I'm just going to go straight, and I'm facing up the x-axis. You can just sort of define an example. So I'm at 0, 0, this is my robot. I just define this, and I'm facing, usually when you draw these pictures, there's like a little circle for the robot's position, and a little line that says facing in this direction. It's facing right up the y-axis. He's going to go for 1 meter, my units are meters, so my f is going to be like, okay, now at the end of this, I'm going to be up here, and that's my expected true position, right? So now what's W going to look like? What's its type? I was like right in front of it. Right, yeah. Let's imagine it's just one dimensional. So my robot can just go up and down the y-axis. What's my W going to look like? What's it look like?
Like an area?
Yeah, okay, so in 2D it's going to be like an area. It's going to be like a little vector, right? X error and my Y error. In one dimension it's going to be real, right? It's going to be plus or minus. It's going to be like, so basically it's saying I'm going to go forward. If I drive for 1 meter per second for 1 second, I'm going to be about, my mean is going to be about 1 meter up, 1 meter from where I was before. And my error is going to be plus or minus 0.6. And you typically characterize that. Like if you really want to be accurate, you would take your robot, you get a really careful measuring tape, and you do that test 10 or 20 or 100 times, and actually characterize the error. Like if I do that, if I send drive forward 1 meter for 1 second, yes, the position of where I am right now, my real position. So let's again assume I'm at 0, 0. Draw this picture again. Right. So it takes an input that. What else is it? What's M?
Is that our landmarks?
Yeah, so let's just say, just to make it really simple, let's make it one landmark. But yeah, it can only be lots of landmarks. One landmark. So specifically, what if I want to draw what M is, I'll write the letter now. What should I draw? What is it? In real life, not with no error, yeah. Yeah, it's an XY position. Okay? So like M sub K, this is landmark number 6, and its XY position is like say over 3 and up. Okay? So I have some deterministic function that says, well look, if I'm here and I know I've got a LiDAR, it's giving me returns, and I've got whatever feature detector back magic I got, but I know what that is too. I'm going to assume, it's going to tell me if my landmark is here, it's going to give me this observation. Plus, and then again, what's V sub K? What's V sub K? Sorry, yeah. So notice the sensor, yeah, notice the sensor. And again, I would do this, the right thing to do is to characterize your sensor, right? So like get a measuring tape and take 100 or 1,000 sensor readings. Or maybe your sensor has a manual and they've done that for you and you're created. Or maybe you just make it up. People do that too. More than you would think. You can often do pretty well by just tuning it by hand. Saying, I don't really know my sensor noise, so it's just be high. It might make it, what happens if I set that to be too high? What will my model do? It's higher than Does that make sense? Think about it in localization. So I assume my sensor error is way too high. I assume that it could be off by 10 meters, but really it's never off by more than like 10 centimeters. Yeah.
Collapse landmarks that are close together in one landmark.
So let's assume data association is solved. I know it's an L. So I'll never do that. I'll never collapse, but I'll always tell you when I say landmark number 6. But I'll always tell you that it's true at this location plus or minus 10 centimeters. But you don't know that. You think it's plus or minus 10 meters. And I try to run my algorithm. What'll happen? What'll it do? I haven't really told you the algorithm. Just try to think about it. When I get a sensor reading, it's really good, but I don't know it's really good. What am I going to do? I think it's really bad, yeah. I'm not going to trust it. Yeah, right. So my sensor reading might be really good, but I'm not going to trust it. I'm going to trust my history a lot more. So as I'm going to be a lot slower to come up. My estimate covariance, which I'm also making, is going to be big. Right? I'm going to tell you, look, here's the data I have. Here's the best I can do where I think I am. That's probably going to be pretty good because these errors are big. My estimated covariance is going to be very high. I'm going to tell you, like, look, I have no idea. I think we're here, but my covariance is like 10 meters, 100, 20 meters wide. I plug in those high covariances. Okay? Even though if I knew my true was 10 centimeters, I could really be much smaller. A much smaller circle. Now let's imagine the opposite problem. Okay? So let's imagine that I tell my model that my sensor noise is 10 centimeters, but really I've got a really noisy sensor. Somebody put a bug, it's a little, they flip a coin and half the time they return random sensor noise. It's a really buggy sensor. Now what's it going to do? Yes.
Is it going to zoom in too quickly? Maybe
Yeah.
it's wrong.
Right. So it's going to trust my sensor a lot. And it's going to be like, oh, you're this great sensor, awesome sensor, tell me where I am. I'm going to believe you. And I'm going to put a really small covariance on my state estimate because I think you're right. I trust you. Because you told me, you, the designer, told me that my sensor noise was really small. So I'm going to give you wrong estimates. Right? So I'm going to think, if you just think of this as localization, I'm going to think that we're here and really we're here. With my sensor error. Okay? So this is kind of maybe gives you some intuition why you can kind of set these by hand. Because if you get too big, you might not converge as fast, but you'll kind of just when in doubt, you set it to be too big and run it and see how it does. Of course, that's theoretically the right thing to do. And there's, whether it's worth the time to do that depends on the application that you're seeing. If you're making a robot that's operating in hospitals and you're trying to sell them for $20,000 a piece, you really want to know, and it takes you 2 days to find out your right covariances, you're going to do it. If you're just playing around with the robot and you just kind of want to play with SLAM, it's too predators and see how it works. Okay? So now we do this, we make these assumptions. I'm not going to go through the math of it, but like you guys are like, and this is not, you guys are with the fast lab, but like basically what happens is you get to a bunch of matrix multiplications of Jacobians. Like I'm not going to go through the math closely, but what it works out is like if I make these Gaussian noise assumptions, where I know my transition and there's Gaussian noise that I'm trying to estimate, I know the covariance on it, and on those noise models, and I do a bunch of math. I apply the sum and product rule, I plug in my Gaussian, I take the derivatives I need to take and stuff, then I get these time updates and observation updates in terms of matrix multiplications. Okay? And it's really, really fast. Because it's matrix. It's parameterized. I'm not doing CPT. I've got this nice functional form. Gaussians are really nice. They're really nice. Okay. But the problem with this was like the first way that SLAM was defined. The problem with this is that you're not making all of the dependent assumptions into your devices. So the thing that FastSLAM said was actually this distribution over the trajectory doesn't really make sense to write it as a Gaussian and assume that it's all independent. What's actually true is, if I go back to that graphical model, graphical model is it actually looks like this. And I can factor my distribution into these two terms, one of which is scary and one of which is not scary. Or they're scary in different ways, which is good because I can sort of use the not scariness of one to compensate for the scariness of the other one. And again, do that back and forth. So this is sort of the math of that. I can factor it into these two parts. Okay? So I have this distribution on all of the landmark locations given the trajectory through the map and my observations. And separately, I have this distribution on the state. On the state given my observations. Two separate parts. And what I can do is say this part is Gaussian. I can make those same Gaussian assumptions that we talked about for EKF, and they're very good. They fit. They match what I think is really going on. I've got some kind of sensor error, and it all kind of works out. And then I get to Jacobians and stuff that you guys are doing in your project. I have to maintain a Jacobian. But for this part, it's scary. I cannot write down a Greek Gaussian form. I can. I make that assumption, and it doesn't work as well. I'm not getting all the power I can get from my data because I'm making an unrealistic independence assumption. So instead, what I'm going to do, or what you guys are doing in your project, is estimating this one with something called a particle filter, where I'm just going to sample trajectories, and alongside each trajectory, I'm going to store the Gaussian, the mean, and the covariance for all the landmarks. And then I'm going to try to do magic, reweighting and stuff, to try to keep the good-looking particles, get rid of the bad-looking particles, and some more tricks to kind of spread out the particles to make sure that I'm looking at all of the likely hypotheses. The flavor of this algorithm goes back to like our simulated annealing. If you remember from the end of the last lecture, it's that kind of algorithm. I'm going to jump around the space. Every particle is a jump. But it's not just like in simulated annealing, it was an XY. Now it's a lot more, right? It's the mean and the covariance of all those landmarks. It is itself a distribution. Each particle is a distribution over lots of maps. And I've got each of those trajectories sampled and apart because I don't have a good analytic form. So doing this basically works really well. So when FastSLAM came out, I think it was the late 90s that the first paper came out about this idea. It basically, SLAM went from like being really sketchy to being like, oh, this works. This is by exploiting this identification. So when you guys see the Gaussians and the Jacobians coming, that's from this term right here. Whereas the particles are in this term right here. And this whole trick, this whole idea that there's like a part that I'm going to do analytically, I'm going to do means and covariances of Gaussians. It doesn't have to be Gaussians, but Gaussians are very popular. Because they're nice, they're convenient for a lot of reasons. And I've got some part that I'm not going to do analytically, I'm going to do particle cover. That's called Localized particle cover. Okay. I could do this whole thing as a particle. Okay, what would that look like? If every single one of those was a particle, what would be inside of the particles? What's one thing that would be inside? What's inside my particles with this function? Where did you guys go with your question? Or yeah. Yeah. Pose. Cross. What's that? Yeah, what about the landmarks? What's that? Is it the position or is it the means and covariance? Yeah, right. So this is the thing. It's the mean and covariance. Distribution on landmarks. Of all landmarks. Right? Got a matrix for each one of those. But then you can write it as one big matrix, right? You do everything with big matrix. That's how you do it if you want to do fast. Okay, so now imagine I wasn't going to do this trick. I wasn't going to do route localizing. I was going to do this whole thing here as a particle. One big particle. What's in my particles now? What does particle 1 comes out of? Yeah, same as before, because that was already the particle filter. I'm not adding anything. So it's the position of the robot over time. But now, what about my landmarks? Somebody else.
Locations?
What's that?
Just like locations?
Yeah,
of
just the
land?
locations.
Yeah.
That's right. That's exactly right. Landmark. Locations. No covariance. This is where my landmark is. Every particle is a hypothesis about the complete map with no noise on it and the complete trajectory. So what is good about this? And what's bad about this? You can tell me something good or something bad.
It was hard to do here, but where's the landmark?
You know exactly where it is, right? Like it's kind of simple. There's not some weird derivatives that need to happen to make this work. I'm also making less assumptions, right? Like I'm not assuming any Gaussian noise on this thing. And if it's not Gaussian noise, this model, this particle filtering framework will be able to handle in theory if I have enough particles. So that kind of leads towards what's bad about it. What's bad about that? Yeah, I might need way more particles, right? I am not, because I'm analytically representing part of this distribution, I need way fewer particles than I would otherwise, than if I was using this sort of flat-out particle conversion to capture this whole space. Okay? So the whole beauty of this trick was like, look, I can factor in these two parts. One part I don't know how to do analytically. It's really hard to do analytically, and we don't know a way to do it. But the other part, it's really easy to do analytically, and we really believe that that's how our sensor noise works. Right? We really think that's what's going on in our model. And so I'm making this independence assumption that the map, the M's are not part of the state, and they're all independent and stuff. And you get to this separate form where I'm basically bouncing back and forth. I'm using this as Gaussians. I can do it analytically with complicated math, but fast matrix operations when I code it up. And this part, which I can't do analytically, so I think the code is actually simpler in a straight-up particle filter. It much more closely follows the Jaynesian version of things when you're doing the sampling and retrieval. But it is, you need a lot more particles to do. through this quickly. I'll skip a bunch of the slides, but I just want to say a little bit about how this fits. This is the semantic map in the video that I showed before. Fits into this whole thing. So we basically wanted robots that could capture human environments. And I'm going to zip up to this is an example we saw in the video already. We basically, this is good. Sorry, I just want to not zip through it, but like select the right slides to show you. So basically, in SLAM that you're doing that we just talked about, we're estimating the metric map, okay? The occupancy map, free space, unknown space, and occupied space, okay? That's all I know. There's a big matrix, and every cell is one of those three values. In this work, we added two more things in it. So the first thing was a topological map. So that's like saying, well, this is one room, and there's an edge between this room and the other room. You can imagine that overlaid on top of the metric. Clustering things into rooms and then having these edges to go in between this notion of space. And you might want that because it enables you to do, you can imagine doing a star search with topological map much more quickly than if you were in the metric map. And then you just got to go from node to node. In the topological map, you only do that in metric space. It's hierarchical. And then on top of that, we have the semantic map. So we have these labels for different areas of the environment. So the semantic map says, well, this room, which is in the topological map, is a hallway. This other room is a kitchen. This other room is a gym. This other room is a lobby. And it maintains a distribution over all of that. So when we sort of write out the, I guess this might be very close. But like, if we go back to, maybe I'll go back to this one. If we go back to this picture here, our state, our M, is modified to have not just the metric map, but also the topological information, and also the semantic information. And we do the same trick of a route localized particle cluster, where we assume that our observations of the semantics are independent of the actual locations of the landmarks. They just depend on the labels associated with them. And when I do that, I come up with like this consistent framework for doing semantic mapping and all those things. Okay? And it uses the same trick of a route localized particle cluster with different parts that are analytic in different ways. So a lot of the work that we did to do this paper, this was like last year, was basically figuring out which parts are we going to do analytically and how are we going to do them. Because we didn't want, for language stuff, we didn't want to do Gaussian. We had to do a multinomial or counts of different words. How do you do topological math? And there's lots of papers about that, so we had to pick one and then implement it in our framework. We did a fairly standard thing, which, like you guys, not exactly what we just talked about, but a fairly standard thing for the metric map. And then how do we put them all together to get these things? The result. All right, so now we're going to finish up with midterm. So I wanted to sort of say why we're doing it first of all. I said a little bit last time. There's a few things. So first, we want to be able to assess ourselves. Of course, we and the rest of the staff. How well are we doing at conveying this information? And so the idea of having a closed book test where you don't get to talk to your friends lets us really see how well you know this material and what we can do, whether or not we're achieving our goals. Same thing for you. So it also lets you have that same assessment. And I think that's almost more important than us, because really at the end of the day, your learning is your own responsibility. You coming to lecture, you're asking the questions, you're doing the projects, you're doing the practical problems. And if you are able to know when you understand and know when you don't understand, you'll make better decisions about how to spend your time in order to learn material better ways. And third, studying actually helps you learn. Like our goal is, well, I think we have the shared goal of you guys learning the material. Studying helps you learn. So if you give you a high stakes exam where you're forced to study, you're forced to do these review problems, it helps you guys put in that time that you need in that sort of control loop of studying if you don't know, doing these practice problems, in order to really learn this material. That's why. It's not just to cause you. And like I said, the best way to study is to do practice. So in that light, I wanted to put up the goals of the course. So the aims of this course are for you to understand theoretical and practical approaches for building intelligent systems. Describe and implement searching and scoring algorithms for producing intelligent things. And we've come through a bunch of those now, searching and scoring, search stuff. And then use artificial intelligence techniques to solve real world problems. We've had experience with that now in these two projects, as well as lots of different examples. Right? You'll take these problems, this knowledge, and go out into your lives, your interns, your research, your career out your ground, and have it be useful. So then we have this sort of act rationally thing. We're going to iterate through all the actions somehow. You can start to think about now breadth first search, depth first search, A-star search. Somehow we're searching through the space of actions. Remember the stuff about formalizing state action spaces. And then we're scoring, right? So you're trying to think about cost functions that we just make up. If we get a lot, we can get a lot. We make up a cost function based on how we understand the problem. But maybe also starting to think about learning these cost functions, right? So this uncertainty is a way of modeling what the robot knows and what it doesn't know, and what's trying to do. So we're searching on this. So here's sort of on-informed search. So abstraction, breadth first search, depth first search. How to implement it, what complexity trade-offs. Form search, so like sometimes adding new information will just do a lot better. There's this trade-off between speed and accuracy. And then we had that whole A-star thing, where like the Dijkstra's algorithm, when we wanted to find the optimal path with different costs. And then we did greedy, where we just went in the rest direction without taking into account finding the optimal path. And then we combined those two to get A-star. Where we were using our heuristic estimate for guaranteed optimality. We're going to be thinking a lot of examples about heuristics, coming up with heuristics, analyzing whether it's a good heuristic or not. Talk about local search. So when we don't want the paths, this is what the NP's problem. We don't really care how we get there. We just need some configuration. That's good. This was also like our simulated annealing guy. We could save the history of jumps, but we don't really care about that history. We can just kind of throw darts and check out how good those darts are. And then there's heuristics on good places to throw the next dart. Okay, and that idea, simulated annealing, that also is how cars work. And it's very coarse abstraction. And then there's Keynesian motivated idea as to why it's different. We sort of saw that in the idea of the block of life. There's the analytic part. Adversarial search, alpha beta pruning, game playing, tic-tac-toe. That is other guy playing tic-tac-toe in class. We did minimax, then we did alpha beta pruning, and we got to not search one of the tree when we could prove that we had already bounded what our adversary could do. We didn't need to search and see if it was something really good we would never get to. Alpha beta pruning. The probability, James. So the sum rule and the product rule. This idea that it's a generalization of first order logic, of predicate calculus logic, and writing down sort of logical proofs, the difference between that and this probabilistic reasoning. Mapping between a problem description and actual equations, models and equations, multinomial distributions. So that was like where we were going from in last class. We had like our A, A1, A2, A3. I'm in the living room or not, I'm in the bedroom or not, in the kitchen or not, but if they're mutually exclusive and exhaustive, I can write it all as one variable. Graphical models. So the particular Bayes nets, we haven't really